Hello everyone, this is part 4 of simple linear regression, where we'll talk about some of the conditions that are required to make our results statistically reliable. If you remember, we got all these results from the previous video and we attempted to interpret the estimated coefficients 0.42 and 0.048. First, I just want to mention that now the x and y's are all in uppercase letters. In previous videos, I've used lowercase letters simply because I was careless. In textbooks, most likely you're going to see uppercase letters because x and y's are treated as random variables. And the textbooks usually use the lowercase letters when they're referring to the realizations of x and y. Okay, coming back to our results here. We saw from the previous video that there can be many ways that make our results to be unreliable, thereby making interpretations difficult. And that's exactly why in this video, we're going to begin to test statistical reliability of the results here. For instance, we're going to examine how reliable 0.048 is in representing the causal effect of x and y. Okay, so that's what we're going to do. And you should first note that 0.42 and 0.048 are actually estimates based on one particular sample with 30 data points. So then you may be wondering what these values are estimating. Well, these numbers are estimates for the beta 0 and beta 1 in this equation in the middle of the screen. 0.048, which is the estimate that we're mainly interested in, is an estimate for beta 1, and beta 1 here represents the true causal effect of our study on exam scores. Or you can also think about it as the true slope of a line that explains the causal relationship between our study and exam scores. Okay, so beta 1 represents the true causal effect. The problem is we don't know what beta 1 is, and that's exactly why we go through all the trouble of analyzing our sample to get some idea of what the true causal effect could be. So our main question for now is, we want to know if 0.42 and 0.048 are reliable estimates for beta 0 and beta 1. And like I said, we're especially interested in knowing beta 1. We want to know how reliable 0.048 is in representing the true causal effect, or beta 1. And in order to figure all this out, let's first talk a bit about this equation that contains beta 0 and beta 1. So I'm going to bring this equation to the top like this. And this equation is showing the relationship between y, exam scores, and x, our studied in the population. Population meaning the entire data possible. And it contains a constant term, which is beta 0, the true causal effect, which is beta 1, and u, which we call the error terms. So you can think about the error terms as the prediction mistakes in the population. So as an example, we have two students in the population, Chris and Jane, and their exam scores can be explained by these two equations. This is the exam score for Chris. This is the hours that Chris studied for the exam. And this is the error for Chris. And of course, since the population data contains all the data possible, our sample with 30 students can also be expressed like this using the data for each of the 30 students in the sample. I made a list here to make everything more clear about the equation. So both yi and xi are considered as random variables and their realizations can be found in the sample. So yi and xi for I equals 1 through n, all of them are going to be considered as random variables, but in your sample you have some specific numbers for them. You have some specific numbers for y1 through yn, and also you have some specific numbers for x1 through xn in your sample, in your data. Those numbers represent realizations for the random variables y and x. But if you're not talking about realizations, both y and x are random variables. Ui for I equals 1 through n are also all considered as random variables, but their realizations cannot be found since beta 0 and beta 1 are unknown. Beta 0 and beta 1 are just constants. Each represents a number that we don't know, and that's why we're trying to come up with estimates for them. So as an example, expected value of beta 1 is simply going to be beta 1 itself, and variance of beta 1 is 0 since beta 1 is just some number. And it's going to be the same thing for beta 0. Okay, so then now that we're talking about the population, you may be wondering what the population looks like on a graph. Well, since we don't have much information about the population at this point, we can't say much other than to first say that there's going to be a straight line with the slope that equals beta 1. Note that the graph is not showing numbers on y and x-axis because we don't know beta 0 and beta 1. The only reason the line is sloping upward is because I think it's fair to say that the causal effect of our studied on exam scores is going to be some positive number. Now, in addition to the straight line, data point for Chris, for instance, can be the one on the left, and the data point for Jane, for instance, can be the one on the right. And this means that the vertical distance between the straight line and the exam scores of Chris and Jane, they represent the error terms, one for Chris and one for Jane. And now imagine you have a very large number of data points in this graph. Whatever you're imagining is one possibility of what the population data looks like on a graph. We don't have enough information about the population at this moment. We'll have a better picture after placing some assumptions on the data later. Now, as I already mentioned, our sample with 30 data points come from the population. And although we don't have much information about the population, we do know exactly what our sample looks like. We already saw it. If you remember, our sample looked like this. And in order to get some idea on the causal effect of our studied, we fit the data points by minimizing sum square prediction mistakes. After calculations, we ended up with this OLS line, and we took the slope of this OLS line to be the causal effect of our study on the exam scores. Specifically, we got all these results from our sample. And as I mentioned already, what we're trying to do here is we're trying to see if all these estimates are somehow representative of this equation at the bottom that contains the true parameters, including beta 1, which represents the true causal effect. In particular, we want to know if 0.42 and 0.048 are reliable estimates for beta 0 and beta 1. In order for our estimates to be acceptable or reliable, some statistical tests need to be passed. Okay, so then what are those statistical tests? Well, we first want unbiasedness and consistency of the estimators. This means that the expected values of our estimators equal the true values, and also that both of our estimators are consistent. Note that both beta 0 hat and beta 1 hat are estimators, and so they are considered as random variables. After you plug in some specific values using a specific sample, you're going to get some estimates like 0.42 and 0.048. But beta 0 hat and beta 1 hat themselves are called estimators, and they are considered as random variables, and we want them to be unbiased and consistent. Those are the first two statistical tests the estimators have to pass. We also need low variance of our estimators in order for the results to be reliable, but we're going to worry about that later. For now, we first focus on unbiasedness and consistency. So then the question is, how do we know if we have an unbiased and consistent estimators? Well, there are a set of assumptions in the data. They're called OLS assumptions on simple linear regression that make our estimators to be unbiased and consistent. In other words, there are mathematical conditions that's going to make our estimators to be unbiased and consistent, which is what we want. So by knowing which assumptions or conditions are needed to make the estimators unbiased and consistent, we also know when and how the estimators are going to be unreliable. So then we'll go over the OLS assumptions now. Note that the assumptions are for cross-sectional data, meaning one observation for each individual, like the sample that we're working with. The first one is random sampling. We're going to assume that the sample, for us that's 30 data points or observations, is taken randomly from the population. This means that any particular data point does not contain any information about another data point because they're all taken randomly. Using mathematical notations, all of this means that each data point xi, yi for I equals 1 through n are independent of one another. Also, since xi, yi's are randomly drawn from the same population, their distributions are going to be the same. Therefore, xi, yi from I equals 1 through n are going to be iid. And for the same reasons, the error terms ui from I equals 1 through n are also iid. The second assumption or condition is that large outliers are unlikely. In math language, we're going to assume that xi and yi have non-zero finite fourth moments. It basically means that most likely there aren't suspiciously high or low values of x and y. Taking our data as an example, if the students in your sample studied mostly in between 0 and 10 hours, but you see one student who has studied 50 hours, then you want to carefully think whether or not that's representative of the population data. Maybe it represents some sort of mistake in data collection. If it were up to me, I would get rid of that outlier before doing any econometrics analysis. Also, in terms of math, we need this assumption when establishing consistency of our estimators. And now we have our third and important assumption, which is saying that for any individual I, given any value of x, hours studied, the expected value of error for that individual is 0. So as an example, expected value of UI given 2 hours of studying equals 0, and also expected value of UI when the student studies 5.5 hours is also going to be 0. And with random sampling, this assumption can be generalized to the entire population. And so if you consider all the error terms of everyone in the population, then given any value of x, hours studied, the mean of errors is going to be 0. And we're going to see this in a graph in a moment. Now, this third assumption also implies that expected value of yi given xi equals beta 0 plus beta 1 times xi. So this is basically saying that for any individual I, given any value of x, the expected value of exam score is going to be given by the equation of a line, which is beta 0 plus beta 1 times xi. Now, this also means that in the population, given any value of x, the mean of exam scores of different individuals will be given by the equation of a line, which is beta 0 plus beta 1 times some value of x. Now, with the 3 assumptions that we talked about, we have a much better picture of what the population may look like. So let's try to understand all of this using a graph now. And this graph is now showing one possibility of what the population looks like under our 3 assumptions. The many blue dots in the graph represent the many observations of different individuals in the population. When I say many observations in the population, for now you can just think about the largest number you can come up with. Also, expected value of y given x gives us the equation of a line, which is the red line in the graph. So plugging different values of x into the equation, you're going to get the red line. Of course, we don't know what beta 0 and beta 1 are, but beta 0 is the y-intercept and beta 1 is the slope of the red line. Now I'm going to explain one by one why this population satisfies the 3 assumptions. First, with respect to random sampling, population should look somewhat similar to the random sample. And if you look back to our sample, it looks very similar to the graph that you're seeing on this page. Note that the larger the sample size, the more similar sample and the population are going to be. Our sample size is only 30, so it's a small sample, but as you already know, all the data is made up, so I simply made the sample and the population to look alike. Also, with respect to the second assumption, large outliers are not likely, and that's why you don't see any outliers here in this graph. Moving on to the third assumption. The third assumption says that in the population, the mean of errors given each value of x is going to be 0. So, as an example, given x equals 2, think about all the errors that lie on the black vertical line. There are large positive errors in this area, and there are also large negative errors in this area. So the mean of errors should be right about there in the middle. Given any value of x, I generated the errors to be symmetrically distributed around its mean. So for this particular population data, yes, the mean of errors is going to be right in the middle where the yellow arrow is pointing. Also, note that given x equals 2, the mean of errors happens to be a point on the red line where the errors take the value of 0. All of this means that the mean of errors is equal to 0 given x equals 2 in this graph. And if you eyeball the entire graph here, you can see the same pattern, which is that the mean of errors is 0 given any value of x. Therefore, this particular population satisfies our third assumption. Also, since this graph satisfies the third assumption, the mean of exam scores given any value of x is always going to be right on the red line. So you can see that for this particular population, both the errors and the exam scores are centered around the red line symmetrically given any value of x. But this does not always have to be the case. You can have errors or exam scores to be skewed to one side and still satisfy our third assumption. And that is exactly why you should note that even with these 3 assumptions, this is just one of many different ways that population can look like. Finally, the third assumption also tells us that you can think about the red line here as the OLS line of the population. So it's basically the fitted line that minimizes the sum of squared errors in the population. I'm going to talk more about this later in the video. Okay, so then this is one example of what the population looks like under the three assumptions. Now let's come back to our third assumption because it's going to tell us more about the population. First, note that the assumption implies this equation by LIE, Law of Iterated Expectations, which then means that expected value of UI equals 0. So this is going to be one implication. What's the intuition here? Well, expected value of UI given xi equals 0 for any value of xi. So that means expected value of UI given xi will be 0 even if we do not condition on some value of xi. Therefore, expected value of UI equals 0. Another way to understand this is to think about all the errors of everyone in the population. Given any value of x, according to our assumption, the mean of errors is going to be 0. So that means if you take all the errors for all the values of x, the mean of all of those errors in the population is going to be 0. And again, that's why our third assumption here implies that expected value of UI equals 0. Now, our third assumption tells us something else. Since expected value of UI given xi is 0 for any value of xi, expected value of UI does not depend on xi. So another implication of our third assumption here is that there is no covariance between UI and xi. That means we'll have covariance between UI and xi equals 0. I'm going to prove all of this using math in the next video. Now from here, note that by definition of covariance, we then have this equation. And since we know expected value of UI equals 0, we're going to end up with this term that says that expected value of UI times xi equals 0. So this is the second implication coming from our third assumption. Now I'm going to pull up these two equations to the top like this. And again, if the third assumption holds, then we get these two equations automatically. Now if I plug in for UI in both of these two equations, I'm going to end up with these two equations at the bottom left. And using these two equations, I can solve for a unique beta 0 and a unique beta 1 that satisfy these two equations. And if I do that, I'm going to end up with these two solutions, one for beta 0 and one for beta 1. So this third assumption alone is telling us that beta 0 and beta 1 are going to be given by these two equations. Now I'm going to pull up our two estimators on the left side of the screen like this so that we can compare them with beta 0 and beta 1 on the right side. As you can see, beta 0 hat and beta 1 hat on the left look somewhat similar to the true constant and causal effect on the right hand side. This is not a coincidence. As mentioned already, these OLS assumptions make beta 0 hat and beta 1 hat unbiased and consistent. Specifically, the two estimators on the left are sample counterparts to the beta 0 and beta 1 on the right hand side, meaning as n becomes large with random sampling and unlikely outliers, the two estimators on the left converge to the true constant and the true causal effect on the right hand side. All of this means that our two estimators are unbiased and consistent. I'm going to show all the calculations or proofs in the upcoming videos. For now, you should focus on the big picture. Also, it's important to note that if assumption 3 holds, then beta 0 and beta 1, the true constant and the true causal effect, can be understood as results that you get by using method of OLS on the population data. So in other words, imagine you have the entire population data. Now find the coefficients that minimize sum of square errors. Those are beta 0 and beta 1, and beta 1 is the true causal effect. And again, like I said, with assumptions 1 and 2, OLS results from the sample converge to these true values with large N. The estimators are also going to be unbiased, so we have both unbiasedness and consistency. Finally, I'm going to go over the last assumption now, which is that our econometrics model is linear in parameters. So usually you'll see this assumption first in textbooks, but I simply forgot about it because it's kind of obvious. And that's the reason why this assumption is going to be the last assumption in this video. Please do keep in mind that we also definitely need this assumption. So in the previous slides, when I said estimators are unbiased and consistent because of the first three assumptions, I'm implying that this fourth and assumption also holds to be true. Yeah, so just keep that in mind because if this assumption does not hold, well then we're also going to have problems. So then coming back to our final assumption, what does linearity in parameters mean? Many people think that this assumption means that we're restricting the relationship between y and x to be linear. But like I said in the first video, econometrics is not restricted to linear relationship between y and x variables. In other words, econometrics can also handle or allow nonlinear relationship between y and x, like the one that you're seeing on this graph. So instead, what this assumption is saying is that the econometrics model is linear in unknown parameters like beta 0, beta 1, and the error term. So as an example, all three of these equations that you're seeing on the left side satisfy linearity. As you can see, the y and x can be transformed. The OLS definitely allows that, but the betas and the error terms remain as they are. To give an example of nonlinearity, these two equations on the right are showing models that are not linear in parameters, right? So you have some complicated looking models where the models are not linear in betas. So to give an example, machine learning methods usually allow for this possibility, while OLS method, we assume linearity in parameters. So one implication is that if the true model is linear in parameters, for example, y truly depends on x, following any one of the models that look like the ones on the left side, then OLS estimators can be used to come up with parameter estimates. If that's not the case, if the model is not linear in parameters, then using OLS estimators will most likely lead to erroneous conclusions or interpretations. And to give you a bit more information about this, one benefit to assuming linearity compared to nonlinearity is that you get closed form solutions, like the equation for beta 1 hat. So that in addition to interpretations, we also know when our interpretations may be accurate and by how much, and so on and so forth. The bottom line is that we understand a lot about our estimates and various aspects of our model. Okay, so that's some benefits to having linearity in parameters and using OLS method. So these four assumptions are what we need for our OS estimators to be unbiased and consistent. And now we're going to conclude with a brief summary. We wanted to know if estimators return statistically reliable estimates. To begin, unbiasedness and consistency are desired. We went over the four assumptions or conditions that make our estimators to be unbiased and consistent. And so with these assumptions or conditions, we have the following. Beta 0 and beta 1 can be understood as parameters that you get by applying the method of OLS on the population. This means that the OLS results that you get using your sample are simply sample counterparts to various unknown parameters in the population. Finally, unbiasedness and consistency are going to be ensured, so we are now getting close to claiming that OLS estimates are reliable. But if any one of these assumptions or conditions is not held, is violated, then most likely the estimators will be biased and inconsistent, which means that most likely the estimates that we obtain from our sample are not going to be reliable. And so obviously interpretations are not going to be so useful, right? Knowing how and when the assumptions are violated and knowing how those violations lead to biased and inconsistent estimators are very important. And hopefully we will go over all of this in the upcoming videos.